So let me start this. We will discuss now about fluid power. When I say fluid power, which law come to your mind? Pascal's law. Good. So what exactly that law is? How it helps in fluid power? So what law says? What it says about transferring power?
Intensive pressure is equal in all the directions.
Fine. So some of you are aware of that. So we'll just cover the basics of those things. So when we talk about or any equipment or any system that come to your mind when we say fluid power?
Hydraulic ram.
Hydraulic?
RAM.
RAM, JCB. Yeah. Nowadays you might have seen those mobile hydraulic platforms. Right?
Hydraulic brakes.
Hydraulic brakes.
Hearts.
But I think rarely it come to my mind when I think of fluid power hydraulic brake. JCB is more common. I think vehicle because you see around and those activities. So let me just quickly start this topic. It's a fluid power. When we say fluid power, we are talking about three things about this technology. So when we say fluid power, how the fluid will get power. So we'll start with the generation. So fluid power has to be generated, or it has basically to be transformed from mechanical to fluid power. So that is generation part. So we'll be thinking of different components that will be used to generate the fluid power. When we say fluid power, means compressed air or pressurized fluid. These are the two things we will be talking about. So once that is generated, once compressed fluid, compressed air is available and then pressurized fluid is available, what to do with that? We cannot directly connect the actuator. Why? We have a pump, we can just directly connect the lines to the actuator. Why? Why we cannot do that?
Control is required.
Control is required, definitely. See, in between we need to have some kind of a control. Right? So there is a source of fluid power, that is generation, and at the end there will be an actuation. In between that you have to exercise the controls. Right? So we will be discussing about generation, controls, transmission, and in between there is a control of a power using pressurized fluids. And when we talk about liquid, we call it hydraulics, and whenever we talk about gas, it is pneumatics. Right? So let me just pose a problem to you. This is a problem where there is a gravity fed magazine. If you see that, there is a gravity fed magazine where there are boxes stacked one over another. We want to eject the boxes from this magazine and push it. Right? So if you can see, there are two actuators in this system. One is basically ejecting a box from the stack, and once it get ejected, there is another a cylinder or actuator that will push it to the bin. In this case, sometimes it may be a conveyor or sometimes it may be a different system. So this is basically a simple problem. If I have to attempt this, if I have to design a system for this, how can I proceed? So I just want to have some input from your end, then I will guide you. So if I have to design a system like this, where I have a boxes stacked, I need to control two actuators, definitely two cylinders in this case, and then it will push it. Then after the first cylinder extended, I have to extend the second cylinder. I am just talking about the common approach. With your current knowledge of
The force
system.
generated by the first actuator may be some higher than the weight of this box.
Weight of the slab.
Correct. So let me talk about the system. So I need to have some source where I have to generate the fluid power. So then, let me start with a pneumatic system. Suppose if we are going to design a pneumatic system for this particular automated system, so we need a compressor. Right? After that, once you have a compressor, what you will do?
FRL unit.
How you run the compressor? Let me come from a generation step by step.
Electric
Compressor will not run itself. So you need to drive compressor. So you need to connect a motor or maybe engine depending on the situation. If it is in a mobile platform, then you will be connecting an engine. If it is in a stationary platform, you will be using an electric motor basically to run the compressor. So that is what the generation has been done. After that, what you have seen in the pneumatic system?
Capacity of motor according to load.
So that is coming, let's come to the specification of the actuator in a second phase. First we try to identify the different components that are required. I am not again talking to the specific component you are looking forward. Broadly what you understand, you will be connecting after the compressed air is available.
That is
Pressure line,
receiver.
high pressure line.
Receiver. How many of you have seen bicycle tire inflating compressor? Yeah. So there is a compressor and then accumulator or a storage tank.
Storage tank.
And so you have to, why we need a storage tank? Why we cannot directly connect control valves and actuator with the compressor directly?
Constant pressure. Constant pressure.
Constant pressure is required. There is a, because of a compressibility of a gas, it requires time to build up a pressure. So whenever you need and in case of an hydraulic system, situation is different. So let me first talk about the pneumatic system. So you need a storage tank where you can store compressed air at certain pressure. So whenever you need that pressure, it will be immediately made available to the system. Right? So after compressor we will be having a receiver, or we call a storage tank. Right? After that we will be using some kind of a control valves, definitely. So control valve, what exactly you are trying to control there? Direction, because we will be controlling the direction of movement of the actuators.
Speed.
What else? Speed also.
Flow control.
Flow control, that is what speed will be controlled by the flow. So pressure also we want to control. Fine. So I am sure that you know much more pneumatics than I am just trying to explain you. So this is something what I just want to, you already know the things. I am just refining those ideas, putting in a well structured way how to go about the system design. So you understand broadly what are the components required, because you are having two actuators in the system. So what exactly you require? You require two control valves, right? Two control valves to control these two cylinders individually, right? So let me just come to this, and this will be a quiz question you will be writing on your sheet. List major components in order of, first for hydraulic system, another for pneumatic system. You have to start from a generation, then control. You can just mention the control valve, it is fine, but then what type of control valve you will be just mention pressure, flow, direction, as you have already mentioned that. Just list down that. You make two column, one side hydraulic system, another side you write a pneumatic system. Right. So major components in both the systems, can you just list down quickly? Yeah. No issue. We will be covering. We will be taking you to that. If you are not able to do that, it's not a issue. So any feedback from electrical people sitting on this side? You know anything about compressor, pump, actuators? Good, that's fine. So I am here basically to train you on that. So there is no need to worry on that. So once you write down, if you don't know, no problem. Fine. We will be just taking the next slide where I will be discussing on the same. Done? So hydraulic system, what you have written first?
Storage tank and oil.
Yeah, reservoir. Correct.
Accumulator.
So we will just come to that, just stop whatever you have written. Let me take you to the slide. Let us discuss component of a fluid power system, and these components are more or less same in all fluid power system. There is nothing going to be changed in between, right. So we will be starting with a tank, a reservoir. As I have mentioned that in case of a pneumatic system, we have a reservoir for pressurized fluid, that is compressed air. In case of a hydraulic system, we will be having a storage of oil at a atmospheric pressure, right. Then you will be having a pump or a compressor basically to convert the mechanical energy into a fluid power energy. So then you will be having a pump to force liquid through the system. Then to drive a pump, definitely you need some source, so that will be a electric motor or a engine. So these three components, tank, pump and motor, is a generation. With these three components I will be able to generate a pressurized fluid, and then comes the control part. So you require different type of valves to control the fluid power, and we are only controlling 3 things. So that is what I am just trying to make design easy. Any complex system or circuit, we are only controlling 3 things. One is the direction of flow, second is the flow rate, third is the pressure. So what exactly we are trying to achieve by this? If I am controlling pressure, what I am trying to control? Force, correct. Force or torque. So that I am going to control with the pressure of the hydraulic oil or pressure of the compressed air, and then flow rate I am going to control speed of actuation. Basically we are controlling with the flow rate, fine. So valves are available for those particular tasks: control the fluid direction, liquid flow direction, pressure and flow rate. So there are only 3 types of valve that we will see in this system, and then to connect all these elements together we require pipings or tubings, fine, and finally the actuator to convert the fluid energy into mechanical energy, fine. So that is the basic components of all fluid power system. Whenever we are designing any of the circuit, we will be starting from the bottom, we will be starting from a reservoir, then pump, then valves, then actuator, right, and connecting them all together. So let me take a quick look at this. So hydraulic system, if you see, I will be starting with a reservoir, then there is a filter required, then there is a pump driven by electric motor. You require some kind of a pressure regulation. So pressure regulator is there or relief valve is there. After that you will be having a control valve. So there you have options to control the system. There are 3 options shown over here: raise, off and lower, and then you will be having an actuator which is doing the actual work. So it is a conversion of a fluid power to the mechanical. So this is a basic hydraulic system, and if I just take you to the pneumatic system, it is basically only the change you can see here is compressor, and after that you will be storing the compressed air. So reservoir is coming after the compressor, right, and then you require something for treatment of the air. Why we need to treat air? Impurities. And what are impurity? What is the major impurity in the air? Moisture, correct, because that it will clog the walls and damage them. So we need to take out the moisture and push the dry air into the reservoir, right? So I think that is what the common pneumatic system. So let us come to the control components. So 3 basic types of control devices. One is to control the direction, so we require direction control valve, right. Second is to control the pressure, so we require pressure control valve to protect the system, to limit the pressure in the system, and third is to control the speed, we require flow control valves, right. Let me just quickly show you a small video here.
Designing a hydraulic system, we saw that between the power supply unit and the drive unit,
So this is the actuator, and then there is a
the
valve.
power control section makes sure that the system actually performs the functions for which it was designed. Valves are the components in the system that control the energy flow, that is, the oil flow. This makes them a kind of interface between power supply and the drive unit. They open the flow path or they close it. They direct the oil flow. They regulate flow rate and oil pressure. Valves come in the form of poppet valves,
So this is a poppet valve, you can see the way it has opened, now it is closed. So there is a moving element which rests against the seat, and then there are
and slide valves.
a spool type of valve. So by just sliding the spool you will be able to block and open the ports, right.
In poppet valves, a sphere or cone is pressed onto the valve seat, closing off the flow passage. Poppet valves are tight sealing and designed mainly as 2- and 3-way valves. In slide valves, pistons open or close flow paths by moving back and forth, thus sealing off or opening bores. The piston needs a certain amount of tolerance, which is why this type of valve doesn't seal as tightly as poppet valves, so they're only used for pressure of up to 315 bar. Slide valves can open or close several flow paths at once. There are various ways of actuating hydraulic valves. Manually by lever, or by foot pedal, mechanically by roller lever, or by spring, or electrically, as in the case of these solenoid valves.
Fine. So you have seen the direction control valves. Let me just take you to the slide now. So when we talk about direction control valve, we are trying to channelize the flow of the fluid in a particular direction. Fine. So if you see here, there is a spool of a variable diameter, and whenever you slide this spool, it will be opening and closing the ports on the valve body. Fine. So there is a valve which has a body on which there are ports where you will be connecting your outside elements through tubings, and there is a spool inside it. So whenever you slide the spool, you will be able to open and close the particular ports of the valve. Fine. So let me just you have already seen these modes of actuating the valve. Fine. So there is a manual mode through lever. Mechanically you have seen through the roller. So cam and roller is there, which will actuate the valve using pilot pressure. So same pressurized fluid will be used to shift the spool. So you can use pilot lines. Whenever a pressurized line used to control the valve, we call it as a pilot line. So there is a pilot pressure through which you can control the valve, and finally the electrical solenoid. So these are 4 modes of actuating a valve. Whenever I say actuating, means shifting a spool inside the valve. Now let me just quickly explain the symbol, how to make a valve symbol. So that will be useful for you. So we always make, so valve may be having, first thing is position. How many minimum position the valve can have? How many maximum? 3. So valve can be either a 2 position or 3 position. It means that the spool inside the valve can be either having 2 positions or it can have 3 positions. So depending on the number of positions in the valve, we will be making number of boxes in the symbol. So let me just quickly draw that. If I have to make a 2 position valve, I will be making 2 boxes. It means 2 position I am representing by a symbol. Right. So it is a 2 position valve. Then there are certain number of ports onto the valve. Right. So that will be denoting ports on the valve. So suppose let me just draw, so 4 ports on this valve, through which you are connecting external elements to this valve. Right. Out of these 2, the 2 bottom one will be through one you will be delivering a pressurized fluid through the valve. So I will be connecting this to the pump, and we call it a P. So pressurized fluid is coming inside the valve through one port, and on other side you will be draining the fluid back to the reservoir. Right. Other 2 sides of the valve or 2 ports of the valve will be using to connect to the actuator. Right. So then you can have actuator, and then I will be connecting these 2 ports to the actuator. Fine. So whenever we draw valve symbol, we always try to show connections to these ports in a default position. That is the first thing you should understand. So when I draw this valve symbol and I have connected actuator and pump on this side of a symbol, it means this is the default position of the valve. So this is, we always show connections to the default position. So, whenever the system is not in operation, whenever your circuit is not working, this is the default position of the spool, or when it is not actuated, when the valve is not actuated, then this is the default position. There is another box shown over there. This box shows the actuated position. Now, what is the difference between the default position and the actuated position? What exactly get changed? The direction of flow will get changed. So, if I have to retract the cylinder, in a default position, can I draw the arrows inside this? So, that arrow will be, so we will be draining the, so if I want to retract, so I will be connecting the pump line to the other side of the cylinder and then draining the other side of the fluid to the reservoir. So, I will draw arrows like this. It means that in the default position, pressurized line is get connected to the rod end of the cylinder and the other side of the oil will come back to the reservoir. So, that whenever the system will start, it will retract the cylinder, fine. What would be the symbol inside the other position? Can you draw on your sheet? Can you draw on your sheet? Yeah, parallel line and especially the direction of arrows I want to see. Yeah. Just do that, because if you understand this, you understand the valves. We are not marking any port on the other part of the symbol. We are assuming that those 4 ports are fixed. Now, if you just correlate with the physical component, the valve body is fixed, valve ports are fixed, they are not going to change. Only thing that is moving is spool inside the valve, right. So, the changed connection when the spool move to the actuated position, we will be drawing those arrows into this. So, first position is basically to retract the cylinder and the actuated position I want to extend the cylinder, right. To extend the cylinder I have to, so we are assuming that pump is here, tank is here, it is already connected. So, pump will provide pressurized fluid onto the piston end of the cylinder and at the same time I will be draining the oil from the other end to the reservoir. So, when I draw these 2 arrows on the second position, that is the actuated position, my valve symbol is complete. So, that way by just looking at the symbol you can understand that what is the direction of flow when the valve is in default position and when the valve is in the actuated position. You can understand the motion of the actuator with this, fine. Now, what is missing on this valve symbol? Yeah, mode of actuation, how this spool is getting shifted. So, then there are 4 modes as I have shown in the slide. You can denote the actuation on this side of the symbol. So, if I am just going to control this with the pilot pressure, I will be making a dotted line and similarly I will be making a dotted line on the other side. So, this is one mode of actuation. Same way you can have a solenoid symbol on this side, same way. So, wherever you are having this actuation, that particular position is controlled by that actuation, fine. So, this pressurized line will be making this particular connection, this side of the connection, and whenever the pressurized line is connected to this side, then these are the connections made, fine. So, that way you have to draw a valve symbol depending on the positions. Now, if I have a 3 position valve, because we have seen that there may be what is the third position? Center position. So, one is basically left, another right and third one is the center, it is a neutral position of the valve, fine. So, sometimes because in this case you cannot stop the cylinder in between, you will be either extending or you will be retracting, fine. There is no third option. If I am just lifting a load, I cannot stop in between somewhere, I can either extend or retract, there are only 2 options available. So, sometimes we require to hold the load in between and then for that we require to have a third position, fine. So, let me just draw a 3 position. Can you draw on your sheet the 3 position valve for the same task? So, once we know there is a 3 position valve, we will be drawing 3 boxes. So, these 3 boxes denote the 3 positions. So, where exactly we will draw P, T, A and B? Center, because that would be the default position. So, I will be drawing P, T and then A and B. These are the 4 ports on this valve. So, I will be drawing like this, right. And then these 2 left and right positions are the actuated positions. So, by default it is a, so and then how the spool is maintained in the center position, you require two springs basically at the two ends of the spool. So, one spring will be on this side, another spring will be on this side, right, and then you can have either manual lever for this. So, I will be drawing the manual actuation, or there may be some other type of actuation. So, because of the two springs on the spool, the neutral position of the center position is maintained, fine. Now, can you draw the same arrows inside these three positions if I am having a actuator connected to A and B? Can you just draw that? So, please complete this valve symbol inside it, so that I will be stopping the actuator in between whenever there is a neutral position, and then other two position, one will be extending. So, I can just write this will extend the actuator and this will retract the actuator. Done? Done? So, this is what I assume you might have drawn this, fine. So, now you understand how to draw a valve symbol, it is quite easy. Nomenclature we need to understand. When I say 4 by 3, what do you understand by 4 by 3 valve? Yeah. So, first when I say can you name this? This is 4 by 3. DCV, it is a direction control valve. 4 by 3, 4 denotes the ports. So, first number denotes the number of ports onto the valve, and the second number denotes the number of positions of the valve, correct. So, 4 by 3, by just looking at the valve you can see number of ports. Can you see the positions inside the valve? Can you see position inside the valve? Yeah, so that is the reason that symbol is always there on the valve. So, whenever you do lab, please have a look at the symbol onto the valve, then you understand what exactly this type of valve is. So, how many positions are there inside the valve, fine. So, this is clear, direction control valve you now understand. Let me come to the circuit or I should say control system. So, when we say hydraulic and pneumatic control system, what exactly we are drawing in the circuit diagram? We are starting, this is basically a signal flow in the pneumatic system or hydraulic system. There are certain inputs it requires. So, either in the form of a valve, push button valve, or maybe a control valve. So, some signal inputs are there, then you will be combining these signals together, doing by some kind of a processing, and then decision of this will be communicated to a signal output section, and finally the command will get executed, fine. So, this signal output is basically communicated to the direction control valve, fine. So, let me see give you an idea. See why I am just showing this signal flow diagram, because this is important in understanding the difference between pneumatics and electropneumatics. The same signal flow is there, but what exactly will get changed in the electropneumatics? Supply will be given, that is fine. So, if I say signal input, signal processing, signal output, and finally the command execution. See, in electropneumatics and pneumatics, power section will remain same. Power section means fluid power section will remain same. That is the reason that we are saying pneumatics and hydraulics. Only signal control section will change, fine. So, power section will remain same and signal control section will change, means how you are combining the signals and how you will be communicating the signals, right. So, that will get changed. What is the interface between the signal control section and the power section? What is the interface between a signal control section and a power section? See, as I mentioned, that power section is basically the fluid power section, fine, and then what is the difference between the what is the component that will get changed in a signal control section and the power, that is basically whatever you are communicating as a decision, and then it will be a interface between the signal control and power. Which valve? Solenoid valve. Direction control valve is basically the bridge. Direction control valve is basically acting as a bridge, because see what we are doing through direction control valve, we are providing pressurized lines, correct, because these two, if you see here, these are the pressurized lines that we are connecting this direction control valve with, fine, and at the same time we are also communicating the signals. In case of a manually actuated, signals are coming in the form of manual force, fine. Whenever I will be controlling this direction control valve movement with the help of a pressurized fluid, then that pressurized line is basically communicating the signal, and whenever I will be using a electro pneumatics, then I will be using solenoid. So, these solenoids I will be communicating the electrical signals, and that will be moving the spool inside the direction control valve, and which will control the power section. So, cylinder is on the power section side, so it will be moving back and forth, but the control of that cylinder will be done by the direction control valve, and the signal control section is communicating the decision to the direction control valve. So, DCV is basically acting as a bridge, I should say interface between the power section and signal control section. So, that is the idea of just showing this figure. So, let me just quickly show you a circuit. Now, you can see the all components marked over here. There are supply elements, or I should say generation elements in the circuit diagram. Then we will have some input elements. So, what are the input elements in the pneumatic system? Input means how you will be communicating your inputs to the system. Compressed air you are not going to provide. Push button, yeah, push button valves are there. So, when we say push button valve, why I am not saying push button switch? See, because when we talk about pneumatics and hydraulics, it is always valve. Valve means same direction control valve, where you will be having some incoming lines and some outgoing, and then you will be applying a force or some kind of an input you are giving. So, push button valve means through push button you will be moving the spool inside the valve, and that will be controlling the output from the valve. So, then you will be having input elements, push button valve, roller valve, that will also. So, whenever your cylinder move forward, how I come to know that cylinder extended fully, because I can place a roller valve at the other end and that valve will get pressed, then it will give a signal to you, right. So, these are basically the input elements, and then I can combine these elements by using different type of valve, and or valves are there. So, there I can give this. So, in case of a pneumatic system, the complete signal control is happening with the help of a compressed air. So, everywhere we are just directing the compressed air. So, if I just press a push button valve, it will just provide a compressed air, right. Similarly, I will be combining the two direction of compressed air, and then deciding whether it has to go to the output or not. So, those are basically and or valves. Finally, after making this signal processing, I will be communicating the decision. So, direction control valve will take only two decisions. If I am having a 2 position valve, either this position will be actuated or this position will be actuated. So, that decision has to be communicated. So, in this case, if you see the direction control valve is getting in this case, so these are input elements, the combination of these inputs finally get communicated to this direction control valve, and then this is controlling the actuator, right. So, this is what the all elements you can see here in the system. Let me show you a more realistic circuit diagram over here. So, if I have to draw a circuit diagram to control a movement of a punch, so that I can make a shape, sheet metal deformation. So, in this case you will be having a reservoir, starting with the symbol of a reservoir. I am just explaining how to draw a circuit diagram. fine. So, in this case you will be starting with a reservoir, then you can draw a strainer here, there is a pump, there is a motor, then finally you will be taking this to the direction control valve, and the other side of the direction control valve is the actuator, and then you will be having some punch connected to this, and there is a die on the other side, fine. So, let me just come to this diagram, and red button you can see now. You have to basically draw what is the symbol of A, you have to draw what is symbol of B, and you have to draw what is symbol of C. For your help, it is already mentioned that A is basically 5/2 pneumatically operated, or I should say pilot operated valve, direction control valve. So, it says 5/2. Then push button valve is 3/2. So, B is 3/2 push button valve, and C is 3/2 roller valve, roller lever valve. B is push button valve. A is direction control valve 5/2. So, if I say 5/2, you can understand there are 5 ports onto the valve and 2 position of the valve. So, you can immediately make 2 boxes. Please make 2 boxes, and then you can see that there are 5 connections over there. So, this is one that is coming from a compressor. So, if you see here, there is a compressed air line, it is coming to this valve as 1, 2 and 4 are on the cylinder side, 3 and 5 are basically exhaust. Yeah. So, same 5 ports you can see on the other position also. So, this is default position in this case, and then you can have another position here also. So, just make 2 division of this. When I say push button valve, it is basically 3/2. So, there are 3 ports, 1, 2 and 3, right, and it is a 2 position. So, you have to draw arrows inside this. So, actuation, if you see one default position in these all 3/2 valves is maintained by a spring that you can see here. There is a spring symbol on this side, and other side is basically a roller for these 3, and here it will be a manual push button, fine. So, that is what you can draw, and A is basically pilot operated. So, you will be having 2 pilot lines, one coming from this side, another coming from this side, right. Drawn. So, because we do not have that much time to discuss how to select the valve and how to go about the functional identification of a particular valve, we will be just going through the circuit here. So, if I have to control a single acting cylinder, or if I have to control a double acting, how many of you understand what is single acting cylinder and what is double acting cylinder? Nice. Yeah, single acting is basically, if I just show you here quickly, we will be having only one port to make the oil flow inside the cylinder, or the pneumatic line is only one. So, we will have only one line on the cylinder, and then right. So, other side you will only have a bleeding port or exhaust, whatever you can say that. So, if something leaks out, then it can, otherwise you will not be able to move the cylinder. So, this is basically the single acting, because you have only one pressurized line connected to this actuator. So, if I have to extend, yeah. So, if I have to extend, I have to provide a pressure to this cylinder, but how I will retract it? So, suppose if the spring is not there, because of the load, because of the external force, it will retract, right. So, then there will be a external force on this side which will push the cylinder back, push the piston inside the cylinder. So, I can only extend this, and the retraction is with the help of a force. That is one case. Another case also you have correctly identified, there will be a spring on this side. So, whenever you provide a pressurized flow inside the cylinder, it will compress the spring, and as soon as you release the pressure, it will go back, right. So, that is the single acting cylinder. In case of a double acting cylinder, we will be having two ports, so that we can freely control the movement of the actuator. So, I will be having two ports onto this cylinder, A and B. So, in this case, whenever you are making oil flow from A inside the actuator, I have to drain the oil from the other side, right, and whenever you want, so this will extend the actuator, and whenever you want to retract it, then you have to make the oil flow from this side and it will come out from the other side. And that is the reason you have seen that in the direction control valves you will be having P and T, both ports are there, right. But in some cases, if you see here in 3/2 valve, if I just show you here, in the 3/2 there is only one line coming out of the valve, fine. So, normally we will be using that to control the pilot line or for the single acting cylinders. So, 3/2 normally we will use to control the single acting cylinders, and whenever we have a double acting cylinders, we will be having 4/2 or 4/3, fine. So, that is how different actuators works. Now, we will quickly have a look at the design parts. Functional requirement is one part, because we have to identify the suitable control valves and we have to just connect them the way we want the functions to be performed, right. So, you will be drawing the reservoir, you will be drawing a strainer, you will be drawing a direction control valve, and then finally you will be drawing the actuator. So, all hydraulic and pneumatic circuits looks like the same, fine, only depending on functionality you will be selecting different type of control valves. Now, once I have functional design available with me, fine, once the functional design is ready, right, how can I identify the specification, how can I freeze the specification of different components, right. Suppose if I take an example of this system itself, if I have to design a press and then I have to design a hydraulic system for this particular press, how I will be finalizing the specification of the actuator, what pump will be requiring, how we will decide the specifications of the pump, and the direction control valve we have already decided. So, we will start with the specification of the job. So, from suppose if I ask you to design this system, what exactly you require, what exactly you should know, force. So, specification of the job is one thing that you are knowing, or it may be given to you as a specification. Now, after that you have to calculate or you have to find out. So, if I just start with from the actuator, let me start from the actuator. What specification of the actuator is required? If I have to buy a actuator, if I have to buy a actuator, yeah. So, bore diameter is one specification, another stroke length, right. So, these are the two specification, one is the bore dia and another is the stroke length, right. So, these two things you have to find out. How you can find out those specifications? So, let me just give you a problem, I will just come to this because of shortage of time. Please just write down this basic specifications given to you here in the same circuit which I have shown you. So, a sheet metal forming press, as I have shown, there is an actuator, fine, there is a punch and die. The shape is to be formed as hemispherical cup of radius 15 centimeter in 2 mm thick mild steel sheet. Force required is 8 kilonewton in this case. So, force is given to you, force is 8 kilonewton. The forming hammer should approach job from a distance of 30 centimeter. So, if I just see that I am having actuator. So, this distance of approach is 30 centimeter and the production rate given is 240 components per hour. Now, I have to identify the specification, I have to find out the specification of different components required to make this circuit, right. So, from where I should start? So, let us freeze the specification of the hydraulic cylinder. So, two things as you have identified that we need to know the bore length, so bore dia and the stroke length. So, bore dia and stroke length, two variables are unknown in this case. Force is known to you. Now, how can I start this? Correct. So, pressure is equal to force also, but pressure is also not known. See, pressure I am not aware of what is the pressure available, of what is the pressure required for this system. So, one unknown is basically if I say bore dia, another unknown is length of the stroke, pressure is also unknown, flow rate is also unknown, right. If I just show you this sheet, so these all variables are unknown. It is a very basic fluid mechanics, I am not just going into the detail. So, I know only force, in this case I know force is 8 kilonewton, that is required. Now, in case of an actuator, either I should know force pressure, or you will be knowing the dia. So, one has to be freezed. So, these two out of these two parameters I have to freeze one parameter. So, we can start with an assumption whichever is available. Suppose if I already know the pressure that I have to work on, so I will be starting with a pressure, or if I am not knowing the pressure I will be starting with an assumption on a bore dia. So, I can assume a bore dia, let us start with a assumption of 50 mm. I can assume that bore dia is 50 mm. So, I will select a cylinder with a bore dia 50 mm. Now, can you calculate the other parameters?
Length having relation with the diameter?
No, length is not going to have a relation with diameter.
Travel distance.
Yeah,
plus
total travel required. Now, as I mentioned that this has to approach from a 30
plus 15.
correct. So, this has to be approached from 30
plus 4.
centimeter and this radius is 15. So, total travel that cylinder has to make is 45. Right. So, total travel that cylinder has to make is 45. So, I will be making this 45 centimeter is the length of stroke. Right. Now, from this pressure you can easily find out once you freeze the diameter of the actuator. What would be the pressure? You can just find out force divided by area. Force is known, that is 8 kilonewton. Area you can find out from the diameter known over here. So, pressure can be easily found out by just force by area. How you can find out the flow rate?
Number of components per hour.
Yeah, number of components per hour are given. So, it means 240 components per hour. So, how much time is available for making one component? How much time is available for making one component? 15 seconds.
15 seconds.
15 seconds is the time to make one component. And how much distance has to be travelled in 15 seconds?
45.
90. 40 because it will extend and then retract. Okay. So, total 90 centimeter has to be travelled by the actuator in given 15 seconds. Fine. So, you can find out the speed of the movement of the actuator or speed of the movement of the piston inside the cylinder. So, V is equal to 90 centimeter is the distance to be travelled and time available is 15 seconds. fine. So, you can just find out V. So, you know now linear speed of the piston inside the actuator, fine, and flow rate will be area into velocity. So, area is known because once you know the diameter over here. So, this is the area and then this is the linear V. So, A into V you will get the flow rate. Let us come to the problem again. So, hydraulic cylinder bore and length you have already found now because D is 50 mm and length is 90 centimeter. So, once you freeze the specification of hydraulic cylinder or hydraulic actuator, next to find out the pump pressure and the flow rate, fine. So, pump pressure is force per unit area you can find out, and flow rate you have calculated from the production speed, that is the components per hour requirement. So, you know the linear velocity and you can find out the flow rate. So, pump selection can be done with the help of these two parameters, speed and flow rate and the pressure, that will help you in finding out the suitable pump for your application. Right. Electric motor HP, suppose if you have to drive this pump you require an electric motor, fine, and then if I assume that 75% pump efficiency, then what is the specification of electric motor? How can I find out what HP motor is required? Because in market if you go you will ask for a particular horsepower motor. How can you find out the what horsepower motor is required to drive this particular pump?
First we should calculate hydraulic power.
Correct. So, first you have to calculate the hydraulic power, pressure into flow rate. So, hydraulic power is pressure into flow rate. So, that much power you require to do the job, and how much electric power you have to give it as an input,
Divided by
0.75.
that divided by the efficiency. So, then you will get the watt of fluid power, watt of electrical power to be given to the pump. I am not considering the inefficiency of the motor right now. Then you can convert into HP, 746, just divide by 746. So, you will find out what is the horsepower of the electric motor required for this particular case. Fine. Reservoir size, what reservoir size I should use? Tank, finally you have to make a tank. How you decide the size of a tank?
Sir, this flow rate multiply by total time, like for 1 hour. Sir, thumb rule is 3 into
Correct.
That flow rate.
So, around 2.5 to 3 times the flow rate in liter per minute. If my system required 10 liter per minute, then my tank should be of 30 liters. That is basically it. So, what basically I am doing, I am storing the oil for 3 minutes of the operation, and that is basically the rule comes out from the industry. So, once I have a flow rate 10 liter per minute, my tank size should be 30 liter, 25 to 30 liter, anything you can have, right. If your system is having much longer fluid lines and it will take more time to get the oil back, then you will be increasing this factor further, right. So, that has been done, reservoir size. Then you can calculate the size of pump inlet and discharge, because tubing also required to be identified. See, what I am just trying to explain is that once you draw the circuit diagram, to physically make that system, you need to know the specification of all the components, then only you can buy and assemble them, right. So, in this case size of pump inlet and discharge tubing you have to find out. So, there is a limitation on the speed or the flow velocity inside the tubing. Why it is so? There is a restriction from a industry for a particular type of oil, you cannot have velocity more than this. This is a limitation. So, suppose if I say 200 meter per second, meter per minute, or 200 centimeter per second, fine. So, if that speed is specified, why we are putting a limit on the speed of a oil flow inside the tubing?
Viscous heating may be there. Viscous heating.
Viscous heating, no, it is related with the oil viscosity, it is not related with the speed as such. If I have a large velocity, then pressure drop
Pressure drop is there.
pressure drop is there, and if the pressure drop below vapor pressure, yeah. So there is a constraint on the inlet velocity and then outlet velocity, right. So discharge tubing has to be decided according to that, inlet and discharge tubing has to be decided according to that speed. So that way once you know all these parameters you can design a system, right. That is what the idea of showing you this particular problem, right. So that has been done over here. Now this is something important because we have started with the assumption that 50 mm dia cylinder has to be used. I can do the same job with a smaller dia cylinder also, even a bigger dia cylinder also. So there should be some reasoning of making a proper selection. So in this case if I use a large dia cylinder, then for the same force it will require less pressure, that is the advantage I should see. But for getting a same velocity I need to have much larger flow rate, right. So that is requires a bigger pump for speed, but it can operate at low pressure. On the other side if I will be using a smaller dia cylinder, then it operates at high pressure because for the same force you require much more pressure because area get reduced now, and the smaller pump because the area is small, so to get the same speed you need to have a lower flow rate. So we have to decide between these two, right. That has been done, I think that is what we have discussed, and in this case pump inlet size we can find out by having this velocity 60 to 150 centimeter per second is the limit on the inlet flow velocity, and on the outlet flow velocity it will be 200 to 450 centimeter per second, right. So from that we will find out the tubing sizes. Now one thing that we have not considered in this system design, the pressure that pump is developing, is the same pressure available at the actuator?
Pressure loss is there.
Pressure losses.
So we have not considered pressure loss in the system till now, right. So we will just quickly have a look at the problem where we will be just calculating the pressure loss, and I would suggest if you can do this problem, you have all your mobiles to do as a calculator. So can we just do that? So you will get an idea how to solve a problem like this. So in this case this is a system. Till now we have not considered the length of the tubings, we have not considered any bend into the system, we have not considered any losses into the system, but when we are concerned about the actual pressure to be found out in this system. So if I am interested in knowing what is the pressure at the inlet of the hydraulic motor, so this is a hydraulic motor here, and I am interested in knowing the pressure that will go inside this hydraulic motor at the inlet. So then I have a pump, I have a piping here, I have tubings basically, and then there are different fittings inside the system. Fittings has been used because you cannot just have straight line pipe that is going from a reservoir to the pump and then pump to the hydraulic motor. So you will be having some kind of a tubing in this case, and then the different length of the pipes will come into picture, right. So in this case we will be calculating the losses, and how we will calculate the loss, which principle you will use? Too much mechanical engineering? Bernoulli's equation, correct. So Bernoulli's equation we will use to find out the velocity and the pressure, right, and losses we will be calculating by using pipe flow equations. Basically the basic pipe flow equations can be used in this case. Through that you can calculate the, it is going more technical, I think so. No problem, fine. So in this case we will be using pipe flow equations to find out the losses. So that, see, this is the realistic system. So first thing, if you see that we have started from a basic circuit based on the functionality, what functions this circuit has to be performed. So we identify the type of valves, we identify the different control elements in the system, we draw the circuit diagram, right. After finalizing the circuit diagram we have find out the specification of the different components, right, and the third part we will be doing the calculation of the losses, because then only your system will be more realistic, right. So, in this case I do not know whether you have time to solve this or not, because it requires some background on this. Yeah, so I will not be pushing you to solve it. Before that, I just want to discuss something that I skipped in between. Yeah, this one. See, when we talk about the design consideration, when we are designing a circuit diagram, in the morning Professor Vadvaji was just mentioning about the safety. So, we are before designing hydraulic system, because these systems are supposed to operate at very high pressure. So, safety is the prime concern we should start with. It is not the functional requirement, we have to take care of the safety inside the system design. So, system design first consideration is the safety. What exactly you will consider inside the safety parts, I will just brief upon that. So, ratings, definitely the different components that you will be using, you will be choosing an appropriate rating for the components. Suppose if I am designing an hydraulic system to operate a furnace door, my system requirement will be different. The functional circuit will remain same. Please note that the functional circuit will remain same, but the cylinder specifications in terms of pressure, in terms of why it is different. What is the problem with the cylinder operating in a furnace area and in this room?
Temperature will be high.
So it's made of metal. What is the problem?
Maybe the property of oil.
Expansion.
Fire hazards, no?
Leakage.
Leakage. Why there is more leakage in the furnace environment?
Viscosity. In hot condition, maybe oil or some material may
Property
get
of oil
changed.
will change.
So, the properties of the oil may get changed. So, one is the specification of the oil, seal. Yeah, that is what something is very important in this case. So, whenever you see an actuator, there is a sealing of a piston inside the actuator body, and this seal is designed for a particular temperature rating only. If you operate the same cylinder in a room temperature and at the furnace environment, the sealing will not going to work. Fine. So, that's the reason that we should choose same thing in the valves also. So, you have to select a proper pressure and temperature ratings of the valve. The next important part is the interlock of interlocking for sequential operations. So, this is a part of a safety. When I say interlocking, what you understand by interlocking?
When one system is running, then another system is locked that system. But that in other country.
So, if I just show you the, if you just recall the first gravity fed magazine diagram, you will be having two actuators. When I say interlocking, interlocking means the second operation will start only when first is over. You will be making sure of that. So, if I just extend the second actuator, assuming that after some time or something like that, you need a feedback. You need to know that the block has been ejected now from the magazine. Now, I have to push it forward, right. So, sequential operation always have to be done one after another. So, first step has to be completed, and you have to put a check in your system that you will be either using some sensors. So, you know that the cylinder 1 is extended, then only the cylinder 2 has to be extended. So, these kind of locks has to be there, and that is very important in case of a sequential operation. You have to design the system for interlocking, right. Then this all we know that there should be an emergency shutdown features, but something is very interesting in hydraulic systems. Emergency shutdown means what? Suppose if you are designing a circuit diagram, I said you have to incorporate an emergency shutdown. What exactly I want to do? My cylinder is lifting a load, and emergency shutdown means what? So, that is something very important to understand. If you just stop the flow of oil, it may not be giving you a safe situation. So, that is what the third position of the direction control valve will help. So, immediately you have to lock the cylinders. So, if I am lifting a load and there is an emergency, I want to stop it, then what will happen? Because of the weight of the load, this will start coming down. Even if you are not pumping oil, there is a movement of the actuator. So, you have to protect that. You have to design a system to take care of that aspect. Most of the time we forgot those aspects. The emergency shutdown means stop the flow of oil, stop the pump. If I say stop the pump, but the stopping pump will not going to help basically in this case. You have to select a proper valve depending on the type of system you are using basically. so that you can either hold the cylinder or actuator wherever it is. So, in case of so you have to think of a proper emergency shutdown features, and that has to be a part of a circuit design, right. Same thing is true with the power failure lock. This is again very important. See, my system is in operation if power fails. So, it is again creating the same situation what you think of as an emergency. Power system power fails means pump will stop. So, when pump will stop, then how your system is going to behave basically. So, in that case that is very important, you have to have a proper power failure locks. See, these features are something different from the functional requirement, you have to, your system should have that. Then operation speed, depending on whatever your functional requirement, you should choose an appropriate speed for the operation. It should not be much higher speed that your system will be running. And finally, the environmental conditions, because if I talk about the hydraulic system, it's oil basically, spillage of oil will definitely harm the environment around it. So, you need to take care of that part. If it is a pneumatic, it will be creating a noise sometimes. So, you should be careful about the pollution, noise pollution that has been created by the system. So, those environmental condition has to be taken care of, means depending. So, most of the cases in pneumatic systems we have a compressor at a different location. So, the noise of a compressor will not come inside this room, right. So, we will be just having tubings which will deliver the compressed air in the room, right. So, that way we will take care of those aspects. So, safety of operation is first thing that you have to emphasize whenever you design a circuit, and then after that we will talk about the functional requirements. Functional requirement, you will make a required selection, whatever desired component that you can have for a system functionality. So, it should meet the required performance specifications. Now, whenever we think about hydraulic or pneumatic systems, they are always be a part of a mechanical system. They themselves independently are not doing anything, fine, because once you have an actuator, it will be performing some operation in the machine. So, this is another very important part, life expectancy is same as a machine. If I am designing a CNC machine, if I am attaching an hydraulic system with that machine, it should not be the case that during the lifetime of a machine the system get replaced. Hydraulic system has to be replaced twice or thrice. You should have, suppose my machine is supposed to work for 10 years, then hydraulic system should also operate for 10 years, right. So, that is important part in this case. Facilitate good maintenance practice, but once you assemble all those components, it will facilitate good maintenance practice. Compatibility with electrical and mechanical components, that is very important in this case. When I have a pump and I want to run with an electric motor, right. So, now there are possibility that I will have single phase motor, I will have 3-phase motor, right. So, if your system should be compatible with each other. My pump shaft dia is different, my motor dia is different. So, you should have a proper coupling requirement. So, all these specification you have to take care, it is not just pressure and flow rate of a pump that will matter, how you will be driving that pump, the specification of electric motor. So, electrical system and mechanical system should be compatible, right. If my system is supposed to operate at 24 volt DC, then that should be made available in the system. I cannot run the valve with a 230 volt AC or whatever source. So, they should be compatible with each other, that is what, and then you have to take care of all operational hazards. You can try to foresee those operational hazards and take care of that part in the system design, right. So, that is what the functional requirement, and last comes the efficiency. So, this is the basically I just want to introduce with the phases. So, first we take care of the safety, then functional requirement, and then efficiency of the operation. I think I should stop over here. Exercise sheet has been circulated, or it is with you, because the exercise that we are going to do in the lab, because the post T will be going to the lab and we will be doing one simulation of this circuit diagram, and physically you will be making yourself those circuits and then making them operational, right. So, a problem has been identified, the same problem that I was just discussing with you, same problem is there on the sheet. So, we will try to attempt the same problem. First, this problem will be trying to build a circuit diagram. First, today we will do with the pneumatic systems or pneumatic components, same problem we will do with the electro-pneumatic system, and same problem we will try to solve with the PLC. So, then you will identify the difference between the different components, right.